Ladies and gentlemen, in this special episode of the Musical Innertube, we will be discussing the movies Twister and Twisters. Spoiler alerts, we'll be talking about a lot of plot twists and questions that arise in the movie Twisters. So if you haven't seen it yet, see it and come back to us. We'll be here.
Hi, everyone. I'm Don Rooney.
And I'm John Timpain.
Welcome to the Musical Innertube, the podcast born out of a mistake.
We once meant to introduce a soothing musical interlude, but we said soothing musical inner tube, and the name stuck.
On this podcast, we talk to interesting people about their interesting lives, jobs, hobbies, and passions.
Difference makers who really make a difference.
And our special guest on the Musical Innertube today to talk about tornadoes, all things tornadoes, and all things twisters, is Carl Parker. Carl is a meteorologist with the Weather Channel based in Atlanta, and he has been doing a lot of work for the Weather Channel on big storms like hurricanes and tornadoes, and he's done a lot of specialty work in research on those two topics. So he's the perfect guy to tell us whether or not twisters could actually work. Welcome again to the Innertube, Carl Parker.
Thank you so much for having me. Nice to join you again.
The original Twister, which I saw in 1996, I started to wonder how people could get so close to a tornado and not be sucked in. And I wondered that again about Twisters when I saw the new movie just the other day. So let's start with that basic question, Carl. How close can you get to a tornado safely?
Well, there are people, there's a trend in chasing, which is, not something that any of us in the professional side condone, which is called zero metering, where they get right into the tornado. There are some people that are equipped to, Reed Timmer and some others have been driving these crazy vehicles. And that was one of the plot points in the newer movie where the truck has, drills essentially that anchor the vehicle. And there are vehicles like that, but they're not just plain old pickup trucks. They're, actually more like tanks, and they're sort of rounded. And, they've got, all kinds of armor and the protection for the windows. That was one of the plot holes in the new movie. Even though, yes, it is a thing to kind of dig into the ground and anchor yourself, you have to have a much, much more reinforced vehicle to do that. I mean, one of the first things that would have happened is the windows would have been blown out of that pickup truck. But in terms of, there are people who have gotten into them. No question about that. That's another of the things that is, not quite right about the movie where, somebody is, right in front of somebody and one person gets, drawn up and another does not. There are plenty of cases where there's a suction force, there's a vertical motion, and you'll see, for example, roofs being taken up and into tornadoes. But when you think about a roof, once there's a little bit of a wind intrusion, then a roof has got a lot of wall space or a lot of, area relative to its weight. So it's one of those things that can be taken up very easily. But in terms of something that's more dense, like a person or a vehicle, you're really going to have to be in the middle of that for that to occur. So, it has happened, and I've seen that. There was actually an incredible video from, I think it was in Dallas from many years ago, where, tractor or trailers from tractor trailers, which again have a lot of, of area, were drawn right up and into a tornado. So, it does happen that way, but I think generally speaking, first of all, more of the motion is horizontal. It's more lateral than a vertical motion, A. And B, if you're that close, pretty much everything is going to be, wiped away in some form or fashion.
Let me ask you about storm chasing and storm chasers just in general. In the late 90s, it was this huge thing. It led, as you know better than we do, to several television shows about storm chasing and storm chasers, many of whom aren't with us anymore, sadly. And I'm wondering whether the function of storm chasers has changed since the first movie in the last 30 years or so? Do they gather as much information as they used to? They used to be the leaders in a way. They used to get new stuff, and there was sort of a race to find out new stuff about tornadoes. I'm wondering if it's still the same today, or are there fewer of them, or are there different ways to find out the same information?
Well, I think there are many more chasers today than there have ever been. You can look, chasers have these geotags, and so you can see, in some cases on big days, hundreds of these out in the plains. And there are many, many people that are doing this. Now, you've got different groups. One is the research side. So that's people from, the National Severe Storms Laboratory and other university organizations that are doing really great work. They've been using what's called the DOW, the Doppler on wheels, where they take this very powerful radar and they get it into the field and they get these incredible radar images of the tornado. So you've got the research side, but then you've got, people that are both meteorologically trained, but also photographers. So kind of, in the middle. And then on another end, you've got people that don't really have a lot of training and they're kind of thrill seekers. And I think that group has really been growing, much to the chagrin of more experienced chasers, because it is inherently a very risky thing to do. There was a case of a guy who, hadn't had much training recently, and he, got into, I guess around the periphery of the tornado, and it ran his car off the road. And you really have to know what you're doing. And even when you know what you're doing, that's not always enough. There was a guy named Tim Samaras,
yes,
who was one of the most experienced chasers around. And he got caught by the El Reno tornado, which was a 2-mile wide tornado, and it had satellite tornadoes spinning around it that were traveling as fast as 185 miles per hour. And, he didn't make it out of there. And he knew everything about everything when it came to tornadoes. So you can only imagine, how people are worried about this explosion of, non-trained chasers who are just looking to put content on social media and otherwise. A lot of us feel that, there's going to be some very serious outcomes as a result of that.
By the way, you mentioned the name of Tim Samaras, who was the subject of a pretty well-watched television series, but also there's a great book about him by Brantley Hartgrove, which I reviewed a couple of years ago, called The Man Who Caught the Storm. It's beautifully written, vividly presented, teaches you an awful lot about how tornadoes form. And you may have some feelings about this book, I'm not sure, but I thought it was a wonderful read, and I'd love to recommend it to our audience.
No, I haven't read that book, but I'm sure that I would enjoy it very much. I would love to read something like that. I am fascinated by the whole tornado mystery, essentially. We have a rough idea of what causes tornadoes, but, we don't understand the very last steps. Why is it that some storms that are, rotating, and that's the first part of it, is you need a rotating storm for these really well-developed tornadoes. Why is it that some of them produce tornadoes and some do not? And that's an ongoing area of research. And it's really fascinating to see. I don't know if you've heard of a guy named Dr. Lee Orff, spelled Leigh. He's got many videos on YouTube, and what he does are these advanced supercomputer simulations of tornadoes. And from this, and they've, checked this against observations in the field. And from this, what we've gleaned is that, a tornado is not really you think of a tornado as a thing, like it's this one thing. And it's not really at all. It's amazing. When you look at these animations, what you realize is that there are these hundreds of strips of vorticity or spin, and they're like, little tornadoes in and of themselves. And what they do is that they're constantly fed into this area where they begin to aggregate, and they just start to all spin around each other when conditions are right. And so, oftentimes when chasers are in the field, you'll hear them referring to a multi-vortex tornado. Oh, we've got a multi-vortex tornado on the ground, where you can clearly see that there are several tornadoes within the larger field that are rotating about each other. But what you can glean from this work that Dr. Lee Orff is doing is that probably every tornado is a multi-vortex tornado, because they're all this collection of these little strips that are rotating about each other, and they're extremely complex. And it's so fascinating because this guy knows so much about tornado dynamics. I mean, he knows it up one side and down the other. And there are points when he's describing his simulations where he'll say, I don't know why that is or what that is. So we're just, we have enough computer power to simulate what's happening, but we can't explain why it's happening. But at the same time, they can relate that to what's being seen in the field, so they know that it's probably, a reasonable simulation of what's happening.
This came up while we were watching Twisters yesterday, when Don and I went to the movie theater, actually, and we're the only people in the theater that we were in, and we were making all sorts of jokes and stuff. But one of the things that did arise, well, it's a movie. Let's just face it. It's a movie you can joke a lot about while it's running, just as
True.
the first one was. This is the big question. How much do we still not know about these tornadoes? I guess the way they form is, it seems unutterably complex, as you've just sketched out, but also they tend to resolve in ways that you don't expect either, which is really heavily leaned on in both movies, the propensity for tornadoes not to do what you expect.
Yeah.
And it's so interesting. It's sort of like flight itself. We know that airplanes fly, but no one can actually explain why they stay in the sky. I mean, we know they do, and we know there must be something going on like X, Y, and Z. But the actual explanation, we ain't quite there yet, and that's got to drive, well, folks like you crazy.
Yeah, well, that's the ball game right there. I mean, that's why, Lee Orff is doing the work that he's doing, and, many other scientists in the field, Karen Kasiba and Paul Markowski, who, by the way, was at Penn State when I was at the station in Harrisburg, WHTM. He was an intern with me, and he ended up being one of the leaders in tornado research. And this is ongoing work that they're doing. I mean, we understand the broad strokes, which are that, you start with wind shear. You have warm and humid air that is feeding into a storm, usually from a, roughly southerly or southeasterly component. And then you've got a flow that is coming across that a little bit higher, maybe at about, 5,000 feet in the atmosphere. And because it's coming across that inflow of warm and humid air, it gets it spinning. And that is then fed into this developing thunderstorm. So the center of the storm begins to rotate, and there's this massive circulation at the center, which is called the mesocyclone, that can extend, miles up into the atmosphere. So you start with this rotating storm, but then there are other storm dynamics that develop, including this balance between that warm and humid inflow and then cooler air, because, once the air rises up through the updraft, then it begins to fall out and precipitate in the front of the storm, and then some of that cool air wraps around the back of the storm as well. So you have what's called the forward flank downdraft and the rear flank downdraft. And tornado-producing storms have a real balance between these forces, that warm and humid inflow in the updraft and the downdrafts. When they maintain a balance between those things, that's when they tend to be more dangerous for tornadoes. But then the downdrafts themselves also factor into this, because as the forward flank downdraft drops down and that colder air hits the ground, well, the cold air is more dense than the warmer air that is coming in. And so the cold air sort of curls around, which you've probably seen this in photographs, where if you have a microburst, the edge of it will form a foot and kind of curl around. And so that curling develops all along that inflow, and that's called the streamwise vorticity current. And that, too, is feeding this vorticity into the storm. So, in terms of these broad strokes, we have a really good general understanding of that. But the question that remains is, why is it that you can have that in some cases and it works to produce a tornado. Why is it that it doesn't in other cases? These are smaller scale features with a very large scale parent storm. That's huge. That's 10 miles across and 10 miles deep and 10 miles high. And that's the part that hopefully we'll be able to resolve in the future. But part of it is also an information thing. I mean, we've got these Doppler radars that are spread all over the country, and it's a very good network, and they're very powerful radars. Developed and that put out, for the most part, they've come online in 1988. But we need a lot more, really. I mean, that's the problem with meteorological modeling too, is you just need more information going in than we have. There are a lot of holes, and particularly in more rural parts of the country, as the Earth is curving away from the radar beam, you're shooting higher and higher into the storm, so you're seeing a much higher part of the storm, and it doesn't tell you what's happening in the low levels of the storm. And that's the business end. That's where the tornado is. And
those rural areas could probably use a lot more coverage, because that's where tornadoes pop up. And that was another thing that came to mind while watching these, and also while actually doing forecasts. And that is that terrain also plays a part in this, because Tornado Alley is across Oklahoma, Texas, into Kansas. Although tornadoes have been known to pop up anywhere. They pop up here in Pennsylvania. They've popped up in New England. How much does terrain play a role in whether or not a tornado pops out?
Oh, it absolutely plays a role. I mean, in terms of very broad features, you've got, of course, the Gulf of Mexico, and so the warm and humid air that comes up into the eastern two-thirds of the country. Then the Rockies play a role, because you have air that flows over the Rockies and then settles down a bit into the plains and creates what's called the cap, which is a layer of slightly warmer air aloft, which suppresses thunderstorm activity until eventually it breaks through and can explode when it finally does. So those are the big things, but also local terrain has a role. There's no question about that. There are little tornado alleys that have developed as a result of terrain. There's one, for example, on the south side of Oklahoma City, and there's a little bit of terrain that most likely is having an impact there. They tend to get tornadoes in northeastern Alabama, of course, in central Alabama, but also northeastern Alabama around Huntsville and up into Chattanooga. And there's been research on that showing that the terrain adds to that environmental vorticity, that it adds to that spin that's getting into these storms. You see a similar thing in your area. There's a little tornado alley that exists more towards the southern part of York County and Lancaster County, and getting out towards the Philly suburbs, more so than farther north. And that was actually a big, there was a big hullabaloo about that many years ago when they decided to put the Doppler radar in State College, because, the people at the then Harrisburg Weather Service office were saying, hey, look, the tornadoes are down here. We should have the radar down here. And I think that was true.
Yeah.
Because, you don't get near the same amount of activity in, say, northern Pennsylvania as you do in that southeastern part of the state.
The other thing that you could say about a storm that produces a tornado is, and you were talking about it in talking about how storms build into tornadoes, there is a little bit of everything in those storms. There's hot air, there's cold air, there's moist air. So you go through a situation, and you do see this in the movies, where it starts as rain, then it goes into hail, and that's where you get some of that the cold moisture coming down, and then just the vorticity that happens when cold and hot meet. It's kind of like if you drop an ice cube on a hot plate. I mean, you're going to get just a huge explosion of energy. And that's one of the reasons why I think probably tornadoes are as volatile as they are, and why they pop up and then go away as quickly as they came.
Yeah, instability is a big part of the question. And, over the years, I've been trying to, find ways to sort of describe that. And so, one of the things I think I actually thought about it when I was in the pool at one time, is that if you have a ball, some kind of a soft rubber ball or something, and you try to hold it underneath the water, well, it's going to try to jump out all the time. And the reason why that is, of course, is that the water is becoming more dense as you go farther down, and the air in the ball is much less dense. So the first thing that the ball wants to do is it wants to get to equilibrium by getting away from the more dense water, down around your waist, and get up to the less dense water that is nearer, where the surface of the water is. So that's why it jumps out all the time. And a similar thing happens in the atmosphere, where you start with this parcel of warm air, and as long as it remains warmer than the surrounding environment, it's going to continue to rise up, to bubble up. And that's how we get deep moist convection developing. And so that's why, meteorologists look for an environment in which, if you were to take that parcel of air and you were to bring it up through the atmosphere and cool it at the rate at which it would typically cool, and it continued to be warmer, and particularly when it's going to be significantly warmer than the surrounding environment because you have cooler air coming in aloft, well, then it's going to continue to rise and rise and rise, and can punch up miles and miles into the atmosphere, and sometimes very rapidly. And so that instability, that convective available potential energy, is a huge part of what we look for. And that is about a supply of warm and humid air at the surface, but also about how the temperature profile changes, how it gets cooler in the upper atmosphere, as it often does when you've got a stronger parent storm coming in.
We'll return to our talk with Carl in just a moment, but first, this soothing musical interlude.
Carl Parker joined the Weather Channel as an on-camera meteorologist in 1999. He joined the expert team in 2011, where he could be found doing in-studio analysis for major weather events. Carl has also been focusing on extreme weather and climate change for several years.
From 1995 to 1999, Carl was with KPRC-TV in Houston, Texas, gathering both personal and professional experience with tropical storms and hurricanes. Prior to Houston, Parker worked for WHTM-TV and WHP-TV in Harrisburg, Pennsylvania. He began his career in 1991 at WTVA-TV in Tupelo, Mississippi, while working on his BS in Geosciences at Mississippi State University. He also has a graduate certificate in climate adaptation from NC State University and holds the American Meteorological Society's seal of approval.
You can follow Carl by tuning in to the Weather Channel or by visiting their website, weathergroup.com.
And now we return you to the Musical Innertube, already in progress. Let's talk about a couple of things specific to the movies. In the first movie, the Twister movie that was released in 1996, the key to the whole thing was that they were trying to put sensors in the middle of a tornado to get readings on wind, on volatility, on moisture, on all these kind of things, which they had never been able to get, according to the plot of the movie, because you can't get inside a tornado. First of all, I know that there were some experiments at the time where they were trying to get scientific material inside tornadoes, and most of those ended in failure because the stuff was destroyed when it got into the tornado. Did we ever get any good readings of what goes on inside a tornado to get data that would help, or are we still just relying on the Doppler radar that takes a map of the whole place?
Yeah, in terms of, actual observations inside a tornado, I know there's been some work on that. I think, probably the more important work is with the Doppler on wheels, which has really painted a very clear picture of the dynamics in a tornado. And then, as I mentioned, some of this simulation work that's been done as well, and all the research that's, associated with or adjacent to that. There's been a lot of, high resolution computer modeling that has, been able to determine, what these dynamics are like. But, as far as, actually, sending up a lot of different, little things into the tornado, I don't know that there's been a ton of that. And I think that is, probably a recoverability issue. When you're talking about a storm that can, send a check for, 50 miles, it's just too hard to do that.
Yeah. And the new movie does have a place where they're putting up the Doppler radar on wheels. They're trying to triangulate it. They're trying to get around a tornado in 3 different areas and get a triangular vision of it. So I'm assuming that has a little bit of a basis in reality.
Oh yeah, absolutely. That's definitely a thing, that phased array radar, where you're getting a more complete picture of the tornado by looking at it from several different sides. They've been doing that in the field for many years.
In the old movie, Twister, they were just trying to get the data. In the new movie, Twisters, the main character has an idea that she will shoot material inside the tornado that will help to dry out the tornado, help to reduce the amount of moisture in there, and help break it up. Is there any scientific data related to that? I mean, is that even a possibility?
Theoretically, there is something to that, but there haven't been any experiments along those lines. And the really important part is that there's so much scale and energy in a thunderstorm. As I mentioned earlier, a severe thunderstorm is in many cases going to be 10 miles, wide, 10 miles high. So you're talking about an area that is 1,000 cubic miles. It is an awfully large area to try to affect. And then when you've got a well-developed tornado, the energy that it's, creating is something on the order of like an atomic bomb every second. So even if you could somehow manage to get, enough of this material into the tornado right at the very right spot, and, you're talking about tons and tons and tons of this material, even if you could do that, maybe it would work for a minute and then fail. So, I just think that it's, that's not, even though it's kind of fun for the movie, that's not really where the research is right now. It's really more about trying to understand the processes. And, once we have a better understanding of what leads one storm to produce a tornado as opposed to another, that's going to increase warning time. But in terms of actually disrupting tornadoes, I don't think that, science is really looking that way.
And there is a common thread between the two movies about trying to increase warning time. How are we doing on that? I mean, what is the current warning time for a tornado? I know there are tornado watches and tornado warnings, and tornado warnings means there's activity that means a tornado is imminent or it's already on the ground. So how much lead time are people in various areas getting? And also, how are we getting the word out? I mean, I know there used to be big tornado sirens that would go off. Are those still in operation?
Yeah, absolutely. Tornado sirens are in place across many, many parts of the country. Increasingly, warnings are going out via phone. People get their local warnings on their phone. I think most people have their phones set that way. And then hopefully they, turn to us or their local meteorologist to get, more information about what's going on. Lead time on average, I think, is about 20 minutes. But obviously there are going to be some cases where things spin up, more quickly than that. And it's all about, initially seeing this rotation, that mesocyclone developing in the, mid-levels or mid to low levels of the storm, because that's, the first thing that shows up. Sometimes it develops so well on radar that you can actually see what's called a tornado vortex signature, which is a much, much smaller feature, usually relative to the mesocyclone, although there are cases where, when you've got a very large tornado that, the whole thing kind of fuses and it's just one, large circulation that's showing up on radar. But, usually we've got a really good idea. If there's a very well-developed tornado that's occurring, it's very rare that you can't see that clearly on radar. And I can tell you from, doing this for now 33 years that, I can look at the radar pretty quickly and make a, sort of snap judgment about, okay, well, that looks like it could do something or oh, there's no question. I mean, I've had that happen to me on the air where I can think of, some cases in recent memory, Rolling Fork in Mississippi, where I'm just looking at it and I'm saying, this is it, folks. Now is the time to, don't try to figure out if it's coming. None of that, get to the most interior room right now. And sure enough, that was a terrible tornado. So, we do have, a pretty good idea of what's coming, especially when it's on the higher end. It's very rare that you get a really strong tornado and that slips by you, in terms of the National Weather Service forecasters who are manning the radar. I also do want to point out that was one of the sort of glaring errors in the movie. For the most part, they did a really good job with the science. They went most of the way there, but there are just a few little things that weren't quite right. But one of the big ones to me was, these two seasoned chasers / scientists that are at the rodeo. And, somehow this massive tornado comes out of the blackness and towards them. And they had no idea that it was coming. That just, that wouldn't happen. It's, first of all, there would have been a warning long before that. And, the sirens would have been on and it just doesn't happen that you get a massive tornado like that. And there's no warning whatsoever. So that was one of the things that strained credibility in a bigger way with that movie.
Yeah, Don and I were really laughing at that point. We said, oh, sure, they're sitting there and there's no warning. And now there's a tornado. I mean, they must really have been rodeo fans and not paying attention to the air, which they're supposed to be so sensitive to, right? Changes in
they'd have to be the worst storm chasers in the history of mankind,
Yeah, but that Glenn Powell sure has nice hair.
I'm telling you, never must. Also, there was no, we got cows in this movie, which is too bad. That's the famous line from the first one, which has gone down in infamy.
Julia, we got cows. Another cow.
Actually, I think that was the same one.
Yeah.
So, all right. Two of the last 3 years in my area of central New Jersey, which is not famous for tornadoes. In fact, we get them very seldom. But 2 of the last 3 years, we've gotten very serious ones. And 3 years ago, we got a tornado that came up Route 1. And luckily, we were watching the Weather Channel when y'all said into the camera, guys, we're counting about 9 to 13 smaller tornadoes and a big one. So if you're anywhere near Route 1, get in your basement, which we definitely did. And we heard that sucker going up Route 1. We could hear it from our house. That's the closest I've ever been. I've never seen a tornado. And so my question to you is, would you have anything to say about the relationship between climate change and tornadoes, where they occur, their frequency? Are we seeing more? Are we seeing a change because the world is changing?
Yeah, in climate science, there's the science of attribution, which is how well we understand how something should be affected by climate change. And then there's detection, which is whether or not we can demonstrate that a change has occurred relative to what's happened in the past. The problem with severe weather is the detection issue is really tricky because we don't have amazing records of what's happened in the past. There's this idea of what's called tornado inflation. The tornado numbers increasing because there are more people that are able to see these, and so more reporting is going on. That having been said, there have been some studies that are showing some different things. One is that we're probably seeing an increase, and we're projected to see an increase in the number of days that are favorable for severe weather, which, makes a lot of sense because, storms feed on warm and humid air. So if there's more of it, then it's conceivable that you could get more severe weather. There's been some research on tornado power, on the power of tornadoes increasing, on the likelihood that outbreaks are occurring more often. Also, we're seeing a shifting in some of the belts, to some extent away from the high plains where it's getting a little bit drier on average and, more towards the Mississippi Valley and parts of the Mid-South. And we're also seeing an increase in tornado activity in the cooler months along the Gulf Coast, which also makes sense because, 40 years ago, December rolls around and, cold air is blasting down from the north and it has shut off the Gulf of Mexico and you don't have to think about tornadoes again until March. Well, now, that cold air kind of ebbs and flows, and then you've got a very warm Gulf. And so when you do get winds out of the south, boom, all of a sudden you're back into a situation where you've got enough warm and humid air, enough buoyancy to support tornadoes. But on top of that, you tend to have really strong parent storms and very strong upper winds in wintertime because they're feeding on the contrast between cold and warm. So, those very strong upper winds are a key ingredient for tornado days. So when you have these vigorous systems coming across, say the Gulf Coast in Louisiana, Mississippi, Alabama, Northwest Florida in the wintertime, and you've got just enough moisture available, well, you can have easily get tornadoes in that case. So that's something that we're also seeing an increase in. So yes, there are some areas where there does appear to be a change in, the frequency of tornado activity or the geography of tornado activity, but it's not as easy to demonstrate as with, for example, obviously heat waves or very heavy rain.
One of the things that we should point out is that you often hear that a tornado is an EF1 or an EF2 or up to 5. And that's a rate of the power of the tornado. But unfortunately, that's one of the things about tornadoes that always got to me, and that is that the scale we use to determine how big and gigantic and powerful a tornado is the amount of destruction that it leaves behind. And that is what those scales are based on. You go and you look at the destruction and figure out in arrears how big it was and how high the winds were. So again, that tells me that we're not any closer to really doing anything about protecting people from tornadoes other than get out of the way when it's coming.
That damage scale was developed several years ago, that enhanced Fujita scale. And, what they did is they got engineers to look at this. They have, many different what are called damage indicators. And these damage indicators are based on the strength of structures. In some cases, it's going to be sort of universal. It's going to be, based on what happens to trees. For example, if trees are debarked or if only a trunk is left, then that's, pretty consistently the sign of a very high-end tornado. But then it's also about the strength of structures. Obviously, manufactured homes are not going to do as well. But there are other, types of, masonry versus, brick versus, siding, whether or not there were clips or anything to hold the structures together. These are all things that they look at to determine the strength of tornadoes after the fact. But what's really interesting is that size and power don't have necessarily that good of a relationship. Certainly, there are cases where you have a very large, extremely dangerous tornado, but there are also very large, weaker tornadoes, especially when they're starting to spin down. You've still got this broad area of winds that's going around, but it's not necessarily that strong. And conversely, you can have what is called a drill bit tornado. There was an amazing video of one, I think it was in Minnesota in the last few years, where it's just this tiny little thing that, might have been, 30 feet across, and it's spinning so fast, it's so powerful. And those can have incredible wind speeds. Howie Bluestein once said that, little spins like that might be supersonic. So there's not always a relationship between size and intensity. And the other thing is, there are plenty of cases where you have very intense tornadoes that occur in a wheat field, but you don't have anything to measure the intensity of the wind in terms of, structural or tree damage. So you never know. unless you had a Doppler radar right on the storm, there was no way to know, what the wind speed is actually. So yeah, it's an imperfect system as it stands right now. But we are gaining a better understanding of how to protect ourselves. And, one of the biggest points of failure in a structure is the roof. Once the roof goes and then you start to drive wind-driven rain into a structure, and it's so much easier for the walls to fail at that point. And that's why there's been a lot of work. There are a number of institutes that have done, really great work on how to reinforce homes. And that can include clips that attach the roof to the walls and make it much more difficult for the roof to come off. And in fact, in Hurricane Michael, which hit Panama City, and I think damaged or destroyed something like 85% of the structures there. There were 5 homes that were built by Habitat for Humanity, and they were built to the highest standard of fortification. And they actually had these long pins that connected the roof through the walls to the foundation. So the roof was bolted to the foundation. And, then they had some other things as well. And the homes were basically unscathed. They had almost no damage among the 5 homes that were in that storm. It was pretty amazing. So we can build to a much higher standard, but, it's going to take a lot of time to do that.
Do we want to go around and give our 0 to 10 rating of Twisters as a movie? I can start.
Go ahead, John.
I can say that as a summer blockbuster that doesn't take any brains, just you want to go in and have a rip snorting time, I'd give it an 8.5. I think, it was fun. As an intense psychological penetrating insight into the reality of human existence, I would give it some sort of decimal just above 0. It's about as deep as a teacup. But, I think we're hearing today that as for the science, it wasn't so bad in many cases. And that might be a reason to go see it. It has some surprises in that way. And it's there for the special effects.
Yeah.
But the science does, it certainly made us ask you some questions that were at least half informed, right?
Yeah, I agree with your assessment completely. Yeah, I think they were pretty good on the science, just, not 100% of the way there. And yeah, I mean, it's, that's the point of the movie is for there to be summer fun. But yeah, you're right. It wasn't a deep penetrating exposition of any kind. Yeah. But that's half the fun of going to the movies, I guess.
Yeah. It was a good way to burn off a box of popcorn and a nice soda. And again, Glenn Powell's hair, perfect throughout the whole thing. What can I say? I mean, for a storm chaser, that guy dresses really pretty nicely. So
yeah, that's funny.
And the title of that book, again, about Tim Samaras, which I recommend to everyone, is beautifully written and very informative about how tornadoes form. Very beautifully done by Brantley Hargrove. It's called The Man Who Caught the Storm, and very much recommended.
And as long as we're recommending that EF scale, that Fujita scale is named after a Dr. Fujita who studied tornadoes for a long, long time and actually came up with a scale. And if you want to learn more about that, PBS has a really nice documentary on that. So if you're one of those PBS passport people and you can go in and look at their old videos, go looking for Dr. Fujita, because it's a really interesting documentary on how he chased down how tornadoes formed. He was one of the first ones to really do in-depth research into that. And Carl, thanks for being on the show today and taking us through what happened in both Twisters and what happens in real life. And hopefully you guys in Atlanta are safe, and we'll try to stay safe up here from the tornado that pops up from now and then.
Absolutely. Thank you so much for having me once again.
And thank you for listening to the Musical Innertube.
Hey, let us know how we're doing. Send us an email at musicalinnertube, all one word, @gmail.com.
Do you know someone with a great story to tell? Let us know. Send us an email or log in to our website, musicalinnertube.com, and click on the microphone in the lower right-hand corner to leave us a voicemail.
And while you're on our website, take a few minutes to listen to past episodes of the podcast. They're all there, along with pictures and biographies of our guests, blog posts, and lots more.
And as always, our thanks to virtual band Car Radio Dog for providing us with our theme music.